I'm really excited to kick off the afternoon session. We have a really great lineup that's going to be super interesting. So we're going to start off with a deep dive on smart tech and national security. This session will focus on the frontier pushing sectors of hypersonics, energy storage, and biosensing. Experts from Sandia National Labs will take a deep dive into essential security considerations when smart tech is used in critical systems, including in energy, aerospace, and healthcare. We'll learn about the varied and profound technical work being carried out at Sandia National Labs, Department of Energy National Laboratory. Dr. Alex Downs will lead the discussion. So over to you, Alex.
Hi, this is Kamlesh Patel. I'm going to go ahead and start off with a few introductory slides, and I will do a quick introduction to the three Sandia speakers, if you don't mind. So I'll go ahead and show my slides, or share my slides. Just a moment. And I'll have my video turn on here. Okay. Hello, everybody. My name is Kamlesh Patel. Thank you for coming to our session today. Hopefully, we'll give you a little bit of perspective of smarter tech in national security. So for those that may not be familiar with Sandia, I thought I'd give you a quick little primer into who Sandia is and what we do. Let me just share my slides real quick. All right. Just curious, can everybody see my slides?
Yes.
Yes. Okay, great. So let's move on real quickly. So Sandia National Laboratories is a multifaceted national security laboratory, primarily in two locations. We have a place in Livermore, California, just next to Lawrence Livermore, you may be familiar with that, and another main site in Albuquerque, New Mexico. And so at the highest level, Sandia is really developing advanced technologies to ensure global peace. Right. And our goal is really to render exceptional service in the national interest. So we break our portfolio into multiple areas to fulfill our national security. Kind of one key area is global security, right? We want to protect against threats against our homeland and across the globe, and all the potential security challenges we have across the entire world that we have. One of our primary missions is around nuclear deterrence, right? We want to ensure that the U.S. National arsenal that we have is safe, dependable, it's reliable, and that we can use that to support our deterrence policy that we have for this nation. A broader category as well is national security programs. And so here we're thinking about more advanced defense technology, intelligence. Some areas related to our cybersecurity portfolio fits into this as well. Another area is energy and homeland security, right? And so here we're thinking about critical infrastructure, environmental attacks, climate change, pandemics, things that really would affect the way of life in the US. And what can we use our engineering and science capabilities to really advance that in forthcoming future? And then finally, the kind of last bucket here is advanced science and technology. Really want to be thinking about science-based engineering, big science, big programs to really push the boundaries of and answer those difficult questions that would be impactful to our science learning and knowledge space that we have. So with that, we were, Sandia is about 15,000 people, and to do this research and development, we really need a great, strong research base of folks, and made up of primarily PhD and masters. And you can see kind of the breakdown of the types of engineers and scientists that we have working together in large multidisciplinary teams to really affect change. So just thought I'd give you that perspective. Today, I'm going to have three speakers that are going to give you perspectives of their research work and their career paths. And we've chosen these speakers to have kind of different positions in their careers that can really go to talk about how they got into Sandia, some of their research influences. And so we'll go with that. Each would be about 10 minutes, and then we'll return back with Q&A. So I encourage everybody to post their questions in the chat, and we'll revisit them at the end. But first, I'd like to introduce Dr. Julia Prager, who will be talking about grid energy storage safety and reliability. Julia, would you mind taking over?
Oh, that was my official cue. Sorry.
Yes, your official cue.
So, hello, my name is Julia, and today I'll be giving a quick overview on my group's work on grid energy storage safety and reliability at Sandia. There we go. First, a bit about me. I grew up in Los Angeles, where the palm trees are. And I was lucky enough to live within 30 miles of JPL. They had an internship program for high school students in that 30-mile window, and I was just within it. My experience there reinforced my interest in doing science and technology work. Then I did my bachelor's in chemical engineering at MIT, and during my junior year there, I did an internship in the corporate research labs at 3M, and it was there that I realized that I needed a PhD to do the sort of work that I was interested in. So then I moved on to the University of Wisconsin-Madison for my PhD in chemical engineering. And then between my bachelor's and my PhD, I also had the opportunity to spend a summer internship in Singapore. And for me, that really reinforced the importance of, or the value of collaboration. So really, there were a series of several key internships that got me to where I was today. Then after my PhD, I moved to Albuquerque, where I spent a year as a postdoc in the energy storage program. And after that, I was converted to staff in the same group, and I'm still there a few years later. I love the people, I love the work. But one thing I wanted to emphasize is, even though I work full-time in Albuquerque, in the last 4 years, I've had significant and amazing opportunities to collaborate with other national labs, universities, and industry in the US and abroad. What's neat is that the sorts of problems that we work on in the energy space are of really broad interest and applicability. Now, getting a bit more into the energy storage side of things, low-cost energy storage is really one of the key assets for modernizing the grid and transitioning to a cleaner electricity infrastructure. It's needed to balance the variability of new renewable generation. It can mitigate billions in commercial losses from outages, and it can reduce commercial industrial electric bills through demand charge management. And for those who are in California, it can also keep the lights on when the grid turns off. Now, batteries are expected to provide a significant amount of that grid-scale energy storage. A 2021 report from the Energy Information Administration estimated that 59 gigawatts of battery energy storage would be on the grid by 2050 in the base case, in black on this plot, and 175 gigawatts if there are more renewables in green. So we all know what batteries are. We have dozens of them in our homes. There's a lot of experience with them in consumer electronics and electric vehicles. But complexity and safety issues increase with battery size. We're moving from watt hours in our small personal devices to megawatt hours and gigawatt hours for the grid. Unfortunately, in the last few years, the safety of battery energy storage systems is a topic that has been getting a lot of media coverage and could serve as a barrier to broader deployment if we get many more headlines like these. Consequently, Sandia's grid energy storage program focuses on all aspects of safety and reliability research, including materials R&D, cell and module testing, simulations and modeling, system-level design and analysis, and outreach codes and standards. And for today's presentation, I wanted to elaborate on 3 different projects that really show the breadth, the different technical backgrounds that are needed to address problems in this space. First, I wanted to highlight a project in the materials science research and development area. One example is our project on solid-state battery safety. So solid-state batteries are batteries without a liquid electrolyte, and they're expected to have more than double the energy density and be safer than lithium-ion batteries. This would advance applications like electric vehicles and energy storage, and also enable new applications like electric aviation. Now, in 2020, we started a program to assess and really probe these assumptions about safety and performance. And one of the key findings, the thermodynamic modeling and calorimetry experiments that we did revealed safety concerns about solid-state batteries. And I show an example of this thermodynamic modeling of heat release versus liquid electrolyte, volume of liquid electrolyte in the battery on the right. A couple of years after we started this program, the operation of over 100 electric buses with solid-state batteries was suspended in France due to fires. So our initial concerns in the lab, questioning these statements about their safety, were unfortunately manifested. Now we have a major new program on solid-state battery safety in collaboration with industry that will impact product development and battery safety testing protocols. So in general, a lot of the work we do, we try to transfer, make it applicable externally. The second project I wanted to share is more software related. Battery data, for example, how batteries degrade under different conditions, different temperatures, different charge and discharge approaches, is needed for many applications. But the raw data from these studies, even those studies from universities and national labs, is typically not shared publicly. To address this problem, we developed the first public repository to compare battery data across institutions using a standard format. That's the website image on the top right, batteryarchive.org. You can go there right now to check it out. And thing that always makes me nervous, because I think during a live talk is that the moment that the site will go down. Hopefully it's up right now. Anyway, we released the open source software package underlying the public site, and you can see those software linkages, the different components of it on the bottom right. We've been excited by the response from the community to this product that we just kind of started bootstrapping. Since the launch, the site has been used by thousands of people from over 70 countries in both academia and industry. Now, the last project I wanted to share is related to community engagement, making sure that all of the research we do reaches stakeholders in the community. Sandia and Pacific Northwest National Lab were tasked in 2014 with forming the Energy Storage Safety Collaborative. This was back when grid energy storage was still fairly new, and they were starting to see grid scale battery fires, and there wasn't a lot of guidance on how to respond. Nowadays, among other things, this group prepares quarterly reports that summarize the status of safety-related codes and standards to companies, to firefighters, to state regulators. You can sign up to if you're interested. Also, we work with the groups that develop codes and standards, like the National Fire Protection Association, IEEE, and Underwriters Lab, to make sure that their guidance is informed by the latest research. So as you can see, advancing energy storage, supporting the grid, these are really problems that need people from a variety of technical backgrounds. Now, none of this would have been possible without the support of the Department of Energy, Office of Electricity Energy Storage Program under the direction of Dr. Imre Zsuk. And we have a large, really fantastic team of across diverse technical backgrounds working on these problems. For more information about the Sandia Energy Storage Program, check out the link at the bottom and reach out to me if you have any questions.
Great, thank you, Julia, for that presentation. I'd introduce the next speaker is going to be Julia Parrish, and she's going to tell us about autonomy in hypersonics. Julia, you have about 10 minutes.
All right, hello everyone. I'm working to share my screen and then we will get going. All right, so today I'll be talking about autonomy for hypersonics. Just real quick, how I got into this area. First, again, starting young, my parents introduced me to model rockets, and I got to fly with my dad, who was an Air Force pilot at a young age, so definitely got that love of aerospace. And then I went to Texas A&M University for all of my degrees, ending with a PhD with a concentration of dynamics and control. And while I was working through my graduate program, I interned at Sandia National Labs. and I actually worked on space systems at the time. But when I graduated, an opportunity to work with rocket systems was available, and I leapt at that opportunity to work, kind of cradle to grave, from algorithms to flight, which is really my dream as an aerospace engineer. So I worked on several different flight programs. I got to go out to launches. I did everything from mod sim to ground testing of attitude control systems to boost guidance, and then ultimately to work on the hypersonic system itself and do guidance and control for that system before I took on the role I'm currently in, which since 2020, right around the time the world was shutting down, I took on a role as the manager for autonomy for hypersonics, which I'll tell you a little bit more about in just a moment. And then outside of all the fun work that I do, I love to go hiking in the mountains here, and just want to share that with my 3 little boys. So for those of you that aren't familiar with hypersonics, I was just going to give a greater than 40,000 foot view of the technology. So if you think of the speed of sound as Mach 1, then hypersonics are generally held to be Mach 5 or higher. And doing the math real quick, that's about a mile per second. So that's kind of the threshold that we use. There's nothing really magic that happens at Mach 5. That's just where we start to see more of these complex aerodynamic, aerothermal, chemical reactions that we have to account for and how they affect the dynamics of the vehicle. And all of that complexity rolled into the dynamics and control challenge is part of the reason that these vehicles are hard to fly, hard to simulate, hard to get right. There are 2 main flavors of hypersonic systems: boost glide systems and air breathers. So for boost glide systems, you can think of this as the rocket provides all of the energy, and then the flight vehicle, the payload, just has to manage that energy till it completes whatever objective it has for the vehicle. Whereas air breathers, they take some of their fuel along, and then they use air as the oxidizer. So they're able to do longer flights, but they typically fly at a much lower velocity. So air breathers are more like Mach 5, Mach 6, where boost glide can get up anywhere to high hypersonic, which is nearly orbital speeds. So when we think about autonomy for these types of vehicles, we have to think about what part of flight they're in, because they cover potentially a very, very large flight envelope. And so you have to think about, is this vehicle exo-atmospheric, meaning outside of the atmosphere or in space? Is it endo? Is it in glide phase? Or is it coming through terminal, which may require it to go through a lot of the flight envelope very quickly? The other thing we have to take into account is what the goal of or the job, the tasking of that vehicle is at any time. Is it mainly sensing? Is it trying to engage a target in a defensive or strike scenario? What is the autonomous kind of tasking for that vehicle? So Sandia has been working in hypersonics for a long time, back to when I was a wee thing with the SWIRV program. And so we had the first successful boost glide flight test back in 1985, and that work was resurrected more recently in the aughts. And we've been working hard to make the system more useful for the warfighter over the years, and that work continues on today as we do further and further development with new capabilities. So you may be wondering, why autonomy for hypersonics? So first, I'm going to explain what we don't mean by autonomy for hypersonics. So when we think of autonomy, we also often think of vehicles like road vehicles, for example, a Tesla. And there are a lot of big differences between how autonomy would be implemented on a Tesla and a hypersonic vehicle, but there are a few things that are the same. So first, that sense, think, act loop is still present in both types of vehicles, where you have to have some data that's coming in that helps you understand the environment and have situational awareness. You have to have some number of decisions points to choose from, some number of actions to choose from, and then you have to execute and then complete that loop again. What's very different from commercial and defense applications is, one, we don't have all of that data coming in. So as I mentioned earlier, hypersonic systems are working through a very adversarial environment, both environmentally and then also potentially there are defenses that they're working through. And when you're working through a very complex type of environment where you have these aerothermal interactions, that can make sensing difficult. You can't put a lot of the same sensors you put on a commercial vehicle onto these types of vehicles. You also have the low swap problem, or size, weight, and power. So you have a limited amount of electronics available, and memory and computational complexity definitely come into play with what kinds of autonomy you can realistically put on these types of vehicles. The other big area is the level of consequence. So when we're talking about a hypersonic vehicle that's potentially in some kind of large engagement, the consequence of autonomous action going awry is much higher than with a lot of the commercial systems that we could potentially leverage for the work that we do. So really have to think about what types of jobs the autonomous hypersonic vehicle is being asked to do, what kind of authority we're willing to delegate it, and what are the consequences for the actions. So we have to put a lot of safing and really think about what is the right way to implement autonomy for these types of systems. So some of the ways that Autonomy for Hypersonics, which is the research portfolio I lead, is looking at implementing autonomy is first looking at trajectory generation. So if you have a vehicle that can move this fast, it takes you a long time to figure out what flight path it's going to take. It's not as useful of a vehicle. So we really have been looking hard at how we can rapidly create new trajectories as well as create them online on the vehicle in real time. Next, understanding how to navigate in challenging environments where you may have sensing modalities that only work in certain parts of flight. So that allows us to have greater utility of the vehicle across the globe. The next is if we really want to think about dynamically utilizing these vehicles, they have to understand what's happening situationally. So, where am I? Navigation, where is my target, what I'm trying to defend against? What are some potential things I'm trying to survive against that are trying to shoot me down? So having that greater contextualization of the environment is something really difficult to do when it's adversarial. And we also want to help the warfighter more broadly understand what's going on in an engagement. And so bringing all that together, we're really working hard to use things like reinforcement learning to understand what tactics we maybe hadn't thought about before, having human biases that allow these vehicles to be more useful, especially in a cooperative context. So Sandia has laid out the Hypersonics of the Future roadmap to guide our research and look at how we can apply autonomy, starting from very relatively simple pre-programmed rules-based autonomy that we can fly in just standard flight software on standard hardware that can go inside our low SWAP vehicle, to start moving to things that require more exquisite sensors, more exquisite communication, and of course, autonomy enabling algorithms, for example, multi-agent reinforcement learning, and using neural networks for image registration and things like that. So really starting to expand the scope that we are applying things like different types of neural network architectures to enable new capabilities on a vehicle. So with that, I'll just wrap up and say that we really are trying to think hard about the future of warfare, how we can deter any future engagements by having a robust capability to respond to them. And that is, using autonomy to increase our ability to respond in a very rapid pace warfare environment, thinking about what we can delegate in terms of autonomy to these types of vehicle and how we can enable shared situational awareness with the warfighter. Thank you.
Thank you, Julie, for that. Introduce our next and final speaker, Alex Downs, who will be talking about microneedles for electrochemical sensors. Alex?
Alrighty, so my name is Alex Downs, and today I'm here to give a little bit more of an early career perspective on some of the bioscience work being done at Sandia. So to first introduce myself, I'm from Arizona. I originally studied biosystems engineering at the University of Arizona, And during that time, I explored a lot of different topics relating to entomology, biosensing, and also biodiesel. But I really was kind of interested in working on biosensing. And I had first kind of gotten my exposure to Sandia Labs during a summer internship over at the Combustion Research Facility at this time, and really liked it just because of the egalitarian nature of research at Sandia.
Julie,
for graduate school,
Alex, real quick, could you full screen your slides? We're seeing the presenter view.
they are full screen to me. Let me try again. Let's see. Yes or no?
Still the same. You might have to switch displays.
Let me see if toggling off use presenter mode works. Again, third time a charm.
Not quite. That's okay. I think we can make it work.
One trick that worked for me is to go to Setup Slideshow. And then that's the button in the top panel there.
Okay, this one.
Oh, I can't see what you're pointing at, but if you click on Setup Slideshow, there's an option to
Fifth icon from the left.
Okay. All right, fourth time is a charm. No.
So Setup Slideshow and then browsed, instead of presented by a speaker, browsed by an individual window.
Okay. Okay. Yes?
Yes.
Okay, excellent, cool. University of Arizona, for my graduate work, I worked in Kevin Plaxco's lab over at UC Santa Barbara. And then after I finished up my PhD, I started a fellowship over at Sandia Labs. So I work in the biological and chemical sensors department, which is different from a couple of the other presentations today, in that we have a very, very broad application space surrounded by chemical and biodetection. So a lot of our work is in chem and biodefense, specifically detecting existing and emerging threats. There's also a lot of basic research in terms of biomarker discovery for disease, healthcare in terms of sensing applications, both for warfighters and for civilians, and a lot of industrial collaborations too. So a lot of times there are industrial startups or different established companies that come to Sandia to help solve problems relating to biosensing and chemical detection. So my personal research background and interests are in biosensing, mainly electrochemical biosensing. So in my PhD at the Plaxco lab, I did a lot of work with aptamers for detection, both in whole blood and different challenging systems like in the veins and in the brains of living animals. Broadly, my interests are in next generation medical diagnostics. So how can we make it easier to get information about what's going on in your body in real time? That goes with either point of care use or with wearable sensing. And as somebody who has been managing autoimmune arthritis symptoms pretty much as long as I can remember, to me, doing immune monitoring is a very, very interesting application that could impact a lot of people positively. So I came here under sort of a unique postdoc. I came under the Hruby Postdoctoral Fellowship, which is one of multiple different Sandia-sponsored postdoc fellowships. So this program is kind of unique because you are technically your PI, so to speak, of your own 3-year funded project. And you have a lot of flexibility to sort of set the scope of that project, collaborate with other people across Sandia, and also travel to present your work. And one thing that I really like is that you have a position to kind of shape research at Sandia by voting on internal research funding committees. So you get to decide what types of grants are funded with internal funding. So my fellowship focus is kind of moving from the very invasive type of in vivo sensing that I was doing during graduate school towards more wearable, minimally invasive applications. So my platform is electrochemical aptamer-based sensors, which are aptamers adhered to a surface. And when they bind to whatever their target is, which may be a protein, it may be a small molecule, it causes a change in electron transfer rate, which can be measured using a range of different techniques. So there's a lot of great things about this platform. It is rapid and reversible, which means that you can measure things in real time, which is very unique in the biosensing field. It works directly in biofluids, which a lot of other things fail when you start putting them in saliva or blood or serum. And these are miniaturizable, so you can make them into very, very small devices. So which is exactly what I've been working on for the past year. So I have been working to miniaturize these to work in a microneedle format, and then demonstrating them in microneedle patches. So why microneedles? They are usually either pain-free or minimally painful. So as opposed to something like a blood draw where you're trying to measure different biomarkers of disease, you can instead do this with very little pain and small sample size. And they enable measurements directly in the body because they are positioned within the dermal tissue. So what this essentially means is a faster sample to answer than blood draws. And what I've demonstrated so far is that these microneedle-based electrochemical aptamer sensors work even when used in body temperature undiluted blood. And when formatted into wearable patch, these are quite easily penetrating the upper layers of the skin and maintaining electrochemical signal within the skin, which is great. So what is kind of next in terms of this research is that I am looking to develop wearable monitoring systems for protein indicators of disease, exposure to biothreats, and also, because of my personal interest, autoimmunity. So to that end, what I'm working on is developing new aptamer sensors for cytokine detection, and then applying them to the microneedle patch platform that I've been working with since I've come to Sandia. And so at Sandia, typically, there's a lot of different application space. There's either kind of more national security, more civilian applications. My work crosscuts between those two because this can be either applied to sort of threat agnostic detection for national security or for the warfighter, as well as healthcare for really anybody through infection and wound monitoring or personalized treatment of different diseases. So I get this question a lot from both undergraduate and graduate students. How does working at Sandia, how is it different from a university? And I feel like one of the largest things is that the teams are very different. So first, you are usually not working on just one topic alone as your little island. You're working on maybe 3 or 4 projects at once with many different people and many different expertise. So the diversity of skills, you'll typically be working with many different types of scientists and engineers as opposed to people in just your discipline. So also you see a lot of changes throughout people's careers. So people may come in as a bioengineer and they may transition into a completely different field entirely, which I really like because I think that it's nice to be able to gain new skills and to constantly be learning things throughout your career. So if you're interested in working at Sandia, there's really a lot of different opportunities at many different levels. So I first got an experience through the SULI program during my undergraduate and then came back as a postgraduate. But there's a number of different well-funded opportunities, regardless of whether you're an undergraduate, graduate, or postgraduate / early career scientist. So if anybody would like to chat about Sandia, kind of from an early career or an intern perspective, I would be happy to chat. Just reach out to me via LinkedIn or at amdowns@sandia.gov. And that's all I got for today. Thank you for your attention.
Thank you, Alex, for that. We have some time for some questions with the 3 speakers. If there are questions, please post them in the chat, or perhaps we can just have you turn on your camera and go live too.
We have a question in the Q&A. It's around the questions of safety.
Yes, I just opened up the tab. Yeah, first from Barbara Gilson. The 2 fires seem to contradict that they were safer. However, maybe there's a thread on that discussion.
There was a question prior to that, since solid-state batteries are safer and are expected to have more than 2 times the energy density of lithium-ion, why use anything else? And my response was, solid-state batteries are an emerging technology, so still a lot of R&D, although there are billions being poured into that R&D. And they were expected to be safer because you're removing the liquid electrolyte that was a fuel for the fire. However, as we saw, just removing the liquid electrolyte is not enough. There's still a lot of work to understand how they respond to different kinds of abuse and failures. And I think this shows how sort of a national lab environment is a good place to do some of that deeper research to challenge some of the initial assumptions in the field.
Thanks for that. Any other last minute questions?
I have a question that was messaged to me from Miriam. What skills do you think are the most important for those looking to aspire for a career at Sandia, and then perhaps specifically in these fields of hypersonics, microneedles, and rockets?
Alex, Julie, or Healy, want to tackle that question first?
I'll start. When I'm also a hiring manager, so some of the things that I look for, I look for first the wheels and the drive. Are you looking to apply and learn and apply what you've learned? Are you a lifelong learner? So that's kind of the wheels. The drive, are you willing to work hard and persevere? Because a lot of the work that we do, they're open-ended problems. There's no textbook answer, right? So if we're going to get to a flight test, for example, there are a lot of moving parts that have to come together. And then the third thing that I really look for is someone that can pitch in and work across bounds. So as an example, I mentioned multiple roles that I had on the flight vehicle. None of those was I ever specifically trained through my education for. I had to pick up and learn, be willing to learn from others, be willing to go out in an area. I learned how to do ground testing of an ACS and, write procedures and things like that I, never learned before. So I think you really have to have that attitude of, we can do this together, and I'm willing to jump in and learn to make it happen.
That's great. Spot on. Alex or Yulia, any comments on that?
I feel like the ability to work respectfully on a team is very, very important at Sandia, and also a flexibility to go outside of your current research space. So a lot of times you may be asked to use your skills for another project, and somebody may say, oh, I need this, come over, for an experiment this week. So being able to communicate across disciplines is also very important.
I have nothing to add to Alex's comments. That was just such a great summary. Actually, when I was brought on board, I remember one of the things that my manager said was, we want people that have the technical ability, but the most important thing is, can they work in a team? Because at the end of the day, no matter how brilliant they are, they cannot tackle these massive projects by themselves. And if they cannot work with the rest of the team, with the people from different backgrounds, just nothing is going to move forward successfully.
Great. Yeah. And I think everybody's spot on. Research is what we do. And I think people who really think about research from a career path do well at Sandia. I encourage folks to go to our career website to look for internship positions, postdoc positions. We do have positions open all the time. So I encourage folks to go to sandia.gov careers to explore, or reach out to one of us. We can help you with that. But I think we're at time. I just want to check in with the moderator and make sure that we don't bump into another session. But thank you again, Alex, Julia, Yulia, for your talks, and welcome any last minute comments, I guess. Or do we have time? I think we're at time, right?
If you'd like to make any last minute comments, we have a few minutes. Closing thoughts?
Well, I would just say that, Sandia National Labs is working very closely with the universities, particularly Berkeley, UC Davis, and the entire California system and across the nation, where we're really trying to build these partnerships with both faculty and students on multiple levels, so that it's not a foreign enterprise of what Sandia does. Yes, national security tends to favor the sensitive information and things to that nature, but there's a cross-section of how advanced engineering, advanced sciences really impact what we do. So we really need the best of the brightest. Diversity of thought is so welcome, because there's no one way to solve a problem. And so we look to have very dynamics and very diverse teams to really bring bear to the problems, because they're not something that just could be solved with a simple textbook or a calculation. So it really requires ingenuity and advanced thinking. So again, at sandia.careers is a good place to go. Please feel to reach out to any of us to learn more about Sandia or opportunities that we have, and we're happy to engage.
That sounds great. Well, thank you so much for coordinating such a great panel. I think it's really representative of the range of kinds of research and kinds of projects that is happening at Sandia. That might be a surprise for some to learn that it is so diverse.